Problem 48, rotate image. We are given a square two-dimensional matrix representing an image, and we have to rotate this image by 90 degrees clockwise. We are told to rotate this image in place, which means we are not allowed to allocate another 2D matrix to assist us with the rotation. So what does that all mean? So first of all, don't be confused by the introduction of this image. There is no actual image. We just have a square matrix given like this. So basically, it's a two-dimensional matrix. So, and we have to simply move these numbers around. So when we're done, this matrix would contain exactly the same numbers, but in different locations. And what would be these new locations? Well, here the image metaphor comes in handy. So imagine that we've rotated this image, this matrix, so that, let's say, if initially you're looking at this matrix from here, that's how I'm looking at this, right? From here. Now, if you were to now look from this direction, you would see numbers exactly in the same spots, right? So for example, this number here would actually move here, and this number would move here, this would move here, etc. Well, and that would come back to here. That's what we mean by rotation, okay? Now, since we're not allowed to allocate another matrix, that means we need to find cycles. And what I mean by cycles is, let's say this number after the rotation moves here, and it's not where it actually will move. I'm just hypothetically saying this. And this number moves here, and then something comes here, and that's then the cycle completes. If this was the case, right, then we don't need to allocate another matrix. We just need to allocate. We can just allocate one variable, a temporary variable, to store, let's say, this last, or maybe, okay, let's call this 23 is the last. So we'll just save this 23. Then we can override this 23 with 46. So 46 would move here. So 23 is gone, is lost, but remember we've saved it. And then 27 would move to 46, but 46 is already in its right place, so it's safe. Then this 4 would come here, and now it's time for 23 to come to this place, but 23 is no longer here, remember? But we've conveniently saved it. So if you have a loop like this, then just by allocating one temporary variable, we could just rotate numbers around this loop. So we need to find loops, all of them, all of the loops, and go through all of these loops once, exactly once. So that's what we're going to do now. So it's possible that this could have been one giant loop, right? So you start rotating and it just goes like a spiral or something, and basically everything just could be just one giant loop. But this won't be the case. I mean, I think you can easily see what's going to happen is, let's start experimenting. So this number will move here. That one in a turn will move here, then here, and this will come back to the beginning and the loop completes. So 4 elements in this loop. And I think that kind of gives us a pattern. So for example, this element would move here, and that 19 would move here, 98 would move to 80, and here again the loop completes. Again, 4 elements. And this will be the pattern. 4 elements. So we can go through all of these loops once, right? We need to, so we somehow have to identify the beginnings of this loop. Now, remember, loops don't really have beginnings, but any one any one element. So if there was a loop, again, this is not an actual loop here, but if there was a loop like this, if I identify one of these things as a beginning, yeah, then I should never touch this, then I should never initiate another rotation of this loop by, for example, starting it again from this point and then this point. That would not be, I mean, potentially, if you go through all of them, you will end up where you started, right? If you, yeah, I think. So if you were to rotate this 4 times and you have 4 elements, so the first time 22 will come here, second time, third time, fourth. So you would end up in the, everything would be in the original spot, you would not rotate anything. And plus you would lose a lot of time. So we need to somehow identify beginning of each loop. So our actual loops will look like this. They will be, you know, the corners of some sort of rectangle, right? So, for example, this rectangle here. So if we kind of look at the top left corner of each of these rectangles and try to identify the top left corner, is that a valid way to say it? Because, I mean, some of them will be heavily tilted. Yeah. Some of them will be very heavily tilted. So what's the top right corner? I mean, is it this one or this one? Well, something like that. I mean, we'll see. You'll see what there will be some rhyme and reason in this. So I propose we work layer by layer. So we kind of approach this matrix as an onion. So we take the outer layer of our onion and just rotate this completely. And you can see that you can, so every element from here would remain on this outer layer when you rotate the image. Yeah, that's clear. Because if I look at this image from here, and then if I look at this image from here, the outer layer should remain an outer layer. Doesn't matter where you look at it from. After you rotate it, it should be. So this wall would become this wall, but it will definitely remain the outer wall. So I propose to go layer by layer and rotate layer. So the outer layer first, and then the next layer inside. Okay, and the next layer, etc. How many layers will there be? Now, if you think about it, let's think about the columns. Let's say there are W columns. W stands for width. So let's say there are W columns. In that case, if you think about each layer containing 2 columns, right? If you strip a layer, then you would strip 2 columns. So W divided by 2 would be the number of layers you can strip away. What if there is an odd number of columns? Well, in that case, there will be one number kind of remaining in between here, in the middle. Yeah. Yeah, well, I currently have even number, but if we had an odd number, there would be, it would not sit in the middle like this, but I mean, there would be a number in the middle, which would be a separate layer in itself. But if we take the floor of W divided by 2, that's the number of layers that we could rotate. I mean, and we would miss rotating this one. We would not rotate this one if we rotate W divided by 2 integer division, so floor of that. But that's fine, because it's a single number. I mean, rotating that single number does not really change its location. So that's the number of layers. Let's write that. First, I'm going to write this part piece by piece, this little program. So I am going to take this function and move it to a slightly better editor in typescriptlang.org, which has a playground for TypeScript. So basically what I need to go through each layer, right? That's what I need to write so far. So for, you know what, why don't I say let width equals matrix length. So this would be the width of the matrix. So now I could say for let layer equals 0th layer, and then layer would be less than what? So we need math floor of w divided by 2, right? And then plus layer. Now, I do not want to keep calculating this thing. I also do not want to, because every time this condition is checked in the loop, this will have to be recalculated. I don't want to do that. So why don't I realize that it does not matter in which direction I go through the loop? I could start layer being equal to this -1. So this value -1, and then just reverse the loop. So layer is greater or equal to 0, and then minus layer. Now this, I could actually, to be honest, speed this up a little bit. This is going to be math floor w divided by 2, exactly the same as if I were to do w binary shift by 1. So if I shift w, right shift, binary right shift by 1 point, this will divide it by 2 and also remove all the fraction bit. So this will take me through all the layers. Does not matter in what order, because each layer is separate. They do not depend on each other in terms of order. So I can just say inside this loop, the variable layer represents one of those layers, and it will go through all of those layers except for this innermost. If you have an odd number of layers, this one number which we don't need to touch, that will be skipped. That's fine. Okay. So let's say we're looking at one of those layers here. Let's say we're looking at this layer. Okay, let's say we're looking at this layer. This is the layer that we are looking at. Oops, sorry. This is the layer, right? So we've removed 2 layers, or we've done 2 layers. That means 2 rows, 2 columns on each side is already processed. So we're now at this 3rd layer, but I mean the index of this would be 2, because we are indexing layers from 0. Now, what I'm trying to say here is I just need starting points. So this is one starting point. This is a second starting point. Third. So these are all starting points for unique cycles. But this next one is not a starting point of a unique cycle, because this is part of this cycle, part of the first cycle. So I can say that the starting point, the row for the starting point is the same as layer, yeah, because that's the row, and it's the same as the index of the layer that we're looking at, because both are 0 based, yeah. How about the column? How about the column? Now, column, there's going to be multiple columns. Column would start from layer, yeah. So that's, the column is layer itself, but then this would be the index of the last element, let's call it L, from here, yeah. So index of the last element minus layer. That would be the index of this element. But we said we don't need this one, right? This is already part of another cycle. So -1. So last element, index of the last element, which is basically W minus 1. W minus 1. Index of the last element minus layer, that would be index of this element, -1. Okay, so we can now do this. So basically we need to go column. Column should be in a loop from layer to this number. So inside, I would say for let column equals layer. Column is less than, you know what I'm going to do, less than or equal to L minus layer minus 1. So L minus layer minus 1. And let me just define constant L equals W minus 1. So L minus layer minus 1 and plus plus column. But here again, I mean, if you see, every time this condition is checked to re-enter the loop, this will be recalculated. I don't want that. So why don't I reverse this loop again? Because in here too, it does not matter in which order we start the cycles. What happens inside the cycle, the order may matter inside the cycle, but in terms of how we go through those cycles, so from one cycle to the next cycle, they're independent. Each cycle is independent. So I could reverse this. I could start, you know, from this value and finish it when this is greater or equal to layer, and then minus minus column. Yeah. So in here, we could say cycle starts at what? Layer column. That is the start of the cycle. Yeah. Why? Because the coordinate, we said row, the row coordinate is layer, and then column coordinate, initially, the column coordinate is the column coordinate. Yeah, layer, column. Yes. So inside this, here, inside the second loop, layer and column will go through all of the starting points of every cycle. So that cycle has 4 elements, 4 nodes, and then we have to just pretty much rotate numbers within these cycles. Okay, let's see how do we rotate that? What do we do there? I think we can remove everything from here. And now we can solely focus on trying to understand. So take one of those cycles. Let's say this is the beginning. Let's say this thing is the beginning. Okay. And let's say now it has a row value. So let's green be row. And what is row? Row is basically this distance here. Row is basically this distance. Or I could say this is row. This distance is row. So the distance from the top. And then I will say red color will be column. And column is this distance. Is this distance. Distance from the left edge, from the left wall. So the coordinates, let's say the coordinates are, green would be for row, and then red would be for column. Yeah? Row and column. Now, when this moves somewhere, when this number moves somewhere, what would be its coordinates? Well, we know roughly what its coordinate will be when you look from here, because its coordinates from here would be kind of the same the same row and column. But our computer is still looking from this direction. So what would our computer see? Computer cannot look at this matrix from a different perspective, right? So in this old frame of reference, what would be the row and column of this new position? Now, you can easily see that, I mean, when you rotate, you know, this red distance, which is measured, from this left wall. Now, this is the left wall, right? So this is the left wall. And this red distance would now be measured from here. So this won't change. This won't change. And then this green distance, which was measured from the top wall. Now the top wall is here when you're looking from here. So the green distance would not also change from top wall. It was this. Now it would be exactly the same. How can we then identify the row and column of this number in the old coordinate system, so to speak? Old frame of reference. So first we need, so we need some sort of row and column, right? Row and column. So what do we write in this spot for the row? Now, row means whatever distance is from the top. But the distance from the top hasn't changed. This is the red bit, and red used to be C. So this C will move here, right? So whatever used to be column will now become our row. Not entirely unexpected, right? How about the column? What should I write in the column spot? Now, in the column spot is going to be this. This is the column. This is this distance here, right? What is that distance? Well, we don't know this distance, but we know this distance. Now, together, they would add up to the index of the last element. Yeah. So L minus the green guy. The green is row. So L minus row. L minus row. I hope you understand what I did here. So maybe one more time for this. So the column again would be this distance, that kind of index from here, from the 0, etc. So we don't know that, but we know this index. We know that this is, so if you were start from 0, 1, this would be 2, right? Whatever it was, whatever your green distance was, whatever your index of the row was. So if this is 0, 1, 2, if you start from 0, etc., together, because these are 0 based, you will get together, if you add them up, you will get the index of this, 0 based index of this, right? You can check this if you want, but this will be, so L minus R. Now, you could also continue this logic and calculate the third value, and then the fourth value. There will be 4 of those in a loop. But I can kind of assure you that the pattern will be the same, because we potentially, the same logic that happened here will repeat. So what will happen is, as you see, the column just moved here. So next time, this column would move here. So you can easily say this will be L minus R. And then what happens here? So, and L minus R moves here, right? So here would be L minus this. Now, this would move here, L minus C. And then L minus this thing. Now, L minus that thing is R, right? And just to complete the loop, just check R would be copied here. Makes sense. And then L minus this would be copied here. and L minus C is just C. So this is correct. Right, so these would be the 4 coordinates of this, then this, and then this. And that would complete our loop. Okay, so what happens now is these coordinates, we can get rid of everything, and basically these coordinates are very important for us. So these coordinates here, we have to move values between here. So like that, and this moves here, and this moves here. Now we could do some fancy loop. We could. I'm not going to do this, but potentially, I mean, you could do some sort of loop. I'm not going to do it because it's not going to be pleasant. There is a temptation to think something like for, let's, like row and column equals, well, we're going to start from layer and column, right? So row and column equals this, and then some sort of entry condition, and then row and column equals column moves here, and L minus row moves here. Yeah. You know what? Let me get rid of this. But there will be some sort of condition here. Yeah, some sort of entry check. There is kind of a temptation to write a loop like this. And you could, with some modification, you could kind of make it work, but it will be pretty large and no faster and no smaller. I mean, there will be no gain if you try to do that. So instead, because there are just 4 numbers, I would suggest that we just do this manually without any loop. This will be faster, and we'll use less memory and all of this. If the cycles were larger, then we could do something. But here I would just avoid doing this. Even though we notice some regularity here and we could write this loop, just ignore it. So what I would do is, let's say I'm just, in my mind, this is the last element, right? So I'm going to save the last element in some sort of temporary variable. So first of all, L minus C and R. L minus C and R. L is my L. C is column. You know what? I'm going to temporarily rename this to C to just match this notation here so that this is confusing enough. So C and row. Now, instead of row, I'm using layer. Layer is row. So I'm going to rename this to R temporarily. I'm going to rename this back. But simply just to keep this. So I'm going to move this value from this location to some sort of temporary variable. So constant temp equals matrix, and what was that? L minus CR. L minus CR. Let's get rid of space here. So I have saved the value of this, whatever is in this location. Now I can override this location by the previous value, right? I can override this location, and I can put there matrix of, what is it? L minus R, L minus C. So L minus R, L minus C. Now I can override this location because this is now kind of saved in its proper place. So that location would be overwritten by C L minus R. C L minus R. Now this location can be overwritten. This will be overwritten by RC. Matrix RC. And now this matrix RC can be overwritten by this, but this is already This does not contain the original value anymore, but we've conveniently saved it in the temporary variable, so this would be temp. So without any loops, these 5 lines would simply basically rotate values within that cycle. Yeah. Now I can rename this back to layer, rename this back to call, which is not a big achievement. C and call, basically the same, but let's keep it like that. So that is that, huh? We don't return anything, so we can take this function back to our thing, replace, and I will try to run this on the pretests. Accept it. Okay, let's submit it. Submitting. Let's see what happens. Okay, accept it. Whoa, we beat 100%. In terms of memory, what? Memory, not that much. Memory beats only 30%, which is incredible. I mean, what the hell did we do here? We just beat 30% of memory. That memory is a little suspicious, but anyway, I mean, I'm happy with this. I'm not going to say this is suspicious. I mean, if we beat 100% of solutions in terms of speed, that's just too nice to be suspicious about it. So our code beat every, so 100.00. How many solutions are there? So there are 2,397,371 out of 3 million. So there are a lot of over 2 million, 2.5 million almost. Nice. That is a decent solution.